Now it's 1 o'clock. Hello, everyone, and nice welcome to come to PRIMaRE first seminar. I'm Professor Jun Jiang. I'm from Unisbat. I'm the current chair of PRIMaRE Partnership. Today, we are going to have two speakers, Professor Ian Masters from Swansea University, and also Dr. Stuart Walker from Exeter University. So probably before they introduce their recent work, I'd like to introduce PRIMaRE very briefly. PRIMaRE is a partnership for research in marine renewable energy. So it is a network of world-class research institutions originally based in Southwest England, Southwest and also Wales, but now it has expanded to include many other institutions as well. So we are aiming to undertake research and development to address challenges facing marine renewable energy sectors, and particularly for the industry at the regional level, nation level, and also international level. So I'll show you how many institutions we have right now. So in the core, that was the original partnership within this PRIMaRE, but now we have expanded. So we have about 17 institutions, including international universities and also industrial partners as well. And also Wave Hub, it is well known, is a field trial test center located in the southwest of England. So the aim of PRIMaRE, we try to provide this forum, a network for research collaborations, mainly in marine renewable energy. So we cover all areas of marine renewable energy. We try to facilitate and also encourage collaborations between partners in universities and also in industry, including both fundamental research, dissemination, and also knowledge exchange. So in the past 10 years, so we have run around 10 conferences, and both we have about 50% is attending the conference from academia, university, academics, and also peer students. Also, we have another half and from industry. So we have really a nice collaboration, a dialogue between academia and also industry. We also run some summer schools and also knowledge exchange workshop as part of a PRIMaRE partnership. Today, we are really pleased to launch our new PRIMaRE seminar series, and we are going to run this quarterly. So next one will be in April, that is 18 April. So if you'd like to come to another seminar, please put this date in your diary. So we are also working very closely with the Southwest Marine Energy Park, and that is representing the industry based in Southwest and also across UK as well. We also have very strong collaboration with Wave Hub. It is a field trial research on the activities. So some other new development is wave energy devices or offshore wind farms. So probably that's a testing center for just the early stage of the research and the development. So we have a lot of excellent facilities and capabilities across these 17 institutions, excellent wave tank in Plymouth University and also other universities as well. And also we have the Wave Hub, and we have Exeter University with the laboratory and also the field trial. And also you can see from the picture here, there are a lot of universities are very, very strong in numerical simulations and they cover many, many different areas, hydrodynamics and the control, structure, reliability, and also environmental impact, and also social economic impact as well. So it's covered all areas in marine renewable energy. So probably this will be my last slide, I guess. So apart from this new PRIMaRE seminar series, we are going to have our 10th PRIMaRE conference that will be held in Bath in June. Is 27th to 28th. It's 2 days of free conference. So call for abstracts is now open and by the 10th March. So you can go to PRIMaRE page to submit your abstract if you are interested to join us conference. That will be in-person conference. This is an online meeting. So today we are going to have two speakers. So first is Ian Master, as Professor Masters from Swansea University. So he's going to bring his talk on remote renewable energy systems is a field trial update. So now over to you, Ian.
Thank you for that introduction, Yun. Let me just share my slides. Okay, can you see that slide okay?
Yeah, that works really well. Over to you now.
Great, okay. So thank you for the introduction. My name's Ian Masters. I work at Swansea University and I've spent around 20 years working on wind, wave and tidal energy technologies. This is a project we have going on at the moment, so the seminar series was an excellent opportunity for us to let you all know about this. Just acknowledge my team, Yestin, Deepak, David, Jose, Tom and Michael. Some of you in the audience know some of those people. They're working on various aspects of the system that we're talking about today. This is within the larger Pembroke Dock Marine project, which is an investment by the City Deal programme to accelerate wind, wave and tidal energy in the Pembrokeshire region, and includes some port developments and some technical activities and also some research activities. So our part of that is the MEIS programme, working with Catapult to work with companies in the local area. And we're using a test site which is run by the Marine Energy Wales team, and that's called META, the Marine Energy Test Area. So that's all our supporters and all our funding. Let me move on and tell you about the technology, hopefully. So we published a paper a couple of years ago outlining the concept design for this turbine. So it's a tidal turbine, and our plan is to put it in the river, in the estuary in Milford Haven very soon. The initial design came from some concepts and some ideas, and our target is really to look at off-grid locations where and remote locations, and that was published in that paper in the Proceedings of the Institute of Civil Engineers. The design concept is to build and maintain with minimal equipment, and it's a mechanical fixed pitch turbine driving a mechanical water pump with an onshore power takeoff using a hydroelectric generator. So the offshore bits, the concept is that the offshore part of the system is purely mechanical and there's no electrical systems offshore, which makes it much easier to look after and maintain. We also have a principle that this system is open source, because we know there's strength in collaborating. And so therefore, we want you to collaborate with us on this technology. Let me just, I've got a very distracting control button at the top. Okay. So the device we're building is not quite the one we published in the paper, and this is using some locally available barge technology. So the barge exists and we're just borrowing it from one of our partners. It's a 10-metre long floating platform with a 2-blade turbine underneath. I'll come back to why it's 2 blades in a little bit later. A water pump power takeoff. It's on a simple catenary mooring. The mooring spreads about 60 metres in 20 metres of water depth. We fitted it with lots of sensors, as many sensors as we think is useful. And just to keep us all going, there's a control cabin where we can run a laptop and other things on top of the barge. So that's the device. We're trying to follow best practice, and there's a technical standard about early stage development, this TS 62600-202, which outlines 4 stages of development for a small scale test. And you evaluate your design and technology readiness level, or TRL, as you go through the stages. And as you iterate around each stage and go on, and in theory, you make sure you don't move on from one stage to the next until you've got all the problems sorted out. We're working against a deadline, so we're having to compress our stages 3 and 4 a little bit, but the first couple of stages have followed that. So the paper I've mentioned is our stage 1, our sort of concept design, and we've just completed stage 2. Let me show you the plan. So the items in green we've already done. So we've done a 50th scale concept design in a flume, we've done a design study, built a model, a virtual model of the system. We've already done a like a stage 1 test where we take a quarter scale power takeoff, tested that on a bench, so a controlled understanding of a power takeoff. We've also completed all of our licensing, consents, risk assessment, method statements for going into sea, and we've completed our design for manufacture stage. So we're currently outsourcing components to be manufactured, and during February we will be assembling this system and putting it in the water. We're starting with an at-sea test of a platform with a small rotor, just to bottom out some of the problems. Then we're going to take the full-scale power takeoff unit on a bench. After that, we're going to deploy some sensors, and then we're going to deploy the barge again with the full-size turbine. And we have a license deadline of 31st of March. So pretty quick timescales at the moment. And I'm hoping to share with the wider world how we get on with this system. So the test site is, as I've said before, is part of META, the Marine Energy Test Area. Marine Energy Test Area have, I think, 8 or 9 sites in and around the Milford Haven estuary in the west of Wales. We're using the Warrior Way site, which is one of the META site which has fast flowing water. For those of you outside of the UK, if you drive west from London for about 4 hours, you get to the other end of the M4, and then you go a bit further and you get to Pembrokeshire. It's about an hour and a half from Swansea, where I am at the moment. The site is a tidal estuary. It's about 20 metres at high water in the location we've chosen, and a tidal range of typically 4 or 5 metres, sometimes up to 10. It's mostly tidal. There are some river inputs to that location. As you can see from the picture on the bottom right, the site is on a bend in the river underneath a fairly steep cliff. For those of you that know Pembrokeshire, that's the high level bridge between Pembroke Dock and northern areas of Milford Haven and Haverfordwest. It's been really good working with the test site. The META team have been great in helping us with our risk assessments, with our marine planning, and all the licensing we've had to do with the Port Authority and Natural Resources Wales, who operate the licensing, environmental licenses for the area. Okay, this is the rotor. It's we've decided to use an existing rotor blade. So our collaborators and colleagues at PRIMaRE have lent us the CAD geometry for the blade used in the famous PRIMaRE papers. And there's some very good comparative data about that rotor in steady state, turbulent and wave conditions. So we've got some good metrics to compare against. It's a NACA profile. We've done some blade element momentum theory predictions of what that rotor might give us. We've checked it with FEA from a structural strength point of view. The funnel element model results are shown there on the picture, and we've outsourced this locally. One of the things about our project is we're funded through the European Regional Development Fund to bring activity into South Wales. So we've used a South Wales-based company to build the blades, and they're using a hand layup glass fibre type approach for that. So nothing particularly clever about the blade design. The eagle-eyed amongst you will have spotted it's a 2-blade rotor, and the PRIMaRE test is a 3-blade rotor. And so we've just looked at that, and what we've done is we've used 2 blades, but we've extended the chord by 1.5 to come back to the original solidity. The difference then in the performance of the rotors is blade tip losses. And so you can see here the difference between the 3 configurations: 2 blades with the original chord, which gives you a slightly higher peak CP at a slightly higher TSR and lower thrust. But if you put the solidity back, you get broadly the same performance, again with the tip loss difference between the two. So that hopefully means we'll be able to make those comparisons. From that, we've looked at some worst case design cases. We ended up with 6 various flow conditions and power conditions and torque conditions. And the items in yellow are the key things we need to worry about, and we've used those to design our system. The thrust at runaway, for example, item 5 there, is used to size the mooring system for the platform. And we have a peak mechanical power at the rotor of about 7 kilowatts. We're expecting slightly less than that at the pump. Because this is a remote location system, we're not too worried about the efficiency of the power takeoff. And so you simply just oversize your rotor slightly for a particular power output. We're looking at robustness rather than efficiency. Okay, this is our first real test, was to build the power takeoff in a small scale on the lab. We've learned a lot from doing this. It's a simple crank arm with a pump. We're pumping water. It's a two-way pump with some one-way valves in it. So we pump on every half stroke. And bottom right of here, there's a sort of a mapping of torque, speed, and pressure on that pump. So we can then translate that back into energy generated from the system. The idea is that the pump would then pump water down a pipeline to shore, and at shore you would either use that water for irrigation or similar, or you run it through a hydroelectric turbine to generate electricity. The thing we're going to do next, once we've built the system, is to deploy it in the river with a small turbine. We've 3D printed some small turbine blades, less than 1 meter in diameter. That's going to allow us to prove our deployment process. We're going to check our mooring load sensors, check our data logging system is working, and we'll just practice doing experiments. And that's with the small power takeoff we just shown you on the bench. And that really is a risk reduction stage. So it's technical risk and also operational risk reduction from doing that. That's only going to be a few days in the water probably. And then we'll decommission briefly, go back to the lab and do the next bit. When we're ready to redeploy a full-scale system, the first thing we're going to do is put some sensors down. We're using a Raspberry Pi based low-cost data logger. Some of you will have heard Tom talk about that in the past. And we are taking lots of measurements around the platform to try and maximize the value of this experiment. We have at least 1 ADV on the platform, probably 2 for taking high quality point measurements. We're going to put down 3 ADCPs, some of those in the right place to use the IEC standard for performance. And hopefully one of them will pick up some wake effects. And on the other side, as you can see in yellow there, is our converging beam ADCP system on the SUSRIF platform. I talked about that at last year's PRIMaRE conference. So we're going to put that unit back in the water and use that to take like a large scale ADV, taking measurements at rotor hub height. We've instrumented the turbine. We're using blade root strain sensors for torque and thrust. We're also measuring RPM, and we're measuring mooring loads from the mooring lines. On the power takeoff pump, again, we're measuring flow rate and pump pressure to give us power out from the pump. And hopefully we'll be able to do some wake measurements using a drone for video measurement and also transects from some sort of vessel. We haven't quite worked that bit out yet. We're going to try and do all of that. Okay, this is the full-scale system design. As I've mentioned before, it's a robust design. So we've gone to fixed pitched variable speed rotor. We have wet running bearings. They sit inside the yellow housings either end of the main drive shaft. The crank mechanism on the left of the slide is a wet running crank mechanism, and that's driving this pump arrangement. And we have closed loop fresh water inside the pump. If we get some leakage from fresh water to salt water, we're not too worried about that, and we should be able to pick that up by monitoring the water levels. That robust design is completely complicated because we want to put some sensors in. So the green bits on the image you can see are the blade root bending sensors and the torque sensors, which take a fairly clean, fairly robust system and add loads of complication. As well as that, we need a slip ring to take data signals out, and we've got an RPM sensor. Those both sit inside a waterproof housing in the center of the shaft, which you can see there as well. So quickly realize that you try and do something simple, and then when you actually want to turn it into an experiment, you have to make it complicated. So that's the system. And I really wanted today to talk about collaboration, and perhaps in the questions and some of the discussion we have in a moment, we can do that. So in March, there's potential for other things to be deployed on the platform while we're in the water. So if that's you, and if you want an opportunity to put a piece of kit on a platform for a couple of weeks, then come and talk to us. You know, we have a platform available. We're also very open to visitors. Obviously, we're going to work out our operational schedules, but if you would like to visit, then you're welcome. We are going to publish the data that we're collecting, and we're going to publish the turbine design and the SolidWorks files. We want to open source this and collaborate. That might take us a little while to happen. So if you want that sooner, please ask us for early access to that data and turbine design. When we've completed this set of trials in March, the platform will be available for other tests. So if you have a different turbine you'd like to test or another type of technology, then again, talk to us and we can make the platform available. And the turbine itself, perhaps in the longer term, we can use it to test other components. It's not that difficult and expensive to change the blades for a different design. We could look at tip features or trailing edge features on a blade design and think about what that looks like. And of course, the power takeoff can be swapped out for other types of power takeoff as well. So all of that opportunity is there, and we're happy to talk to people about some of those opportunities and what's possible after we finished our testing. So that's the collaboration we're hoping to have with people. Again, I'm very open for conversations about those things. So what have I learned so far? And we haven't even got this in the water yet. So the first thing I've learned is field testing is complex and complicated and requires lots of different layers of information. We've been working through those now for the last 6 months, and we're almost there. And of course, once we get to the water, everything will change again. We learned quite early on that putting a turbine in the water is the easy bit. It's only of value when you've got lots of data, and the sensors are not cheap and they're not easy to configure. So we really are trying our best to get some good quality data from this platform design. I'd like to thank our team at Pembroke Dock Marine, Meta, Catapult, and Rudders Boatyard, and our other local suppliers that are helping us with this development. Like I said, we're aiming to collaborate and open source. And over the next couple of months, my plan is to put updates to this technology on Twitter. And there's my Twitter handle. Thank you very much.
Thank you, Ian. Have you finished your presentation?
I have. I thought I wanted to leave plenty of time for some questions and discussion.
Okay, that's great. Yeah, excellent. Congratulations to this great project, and thank you for sharing that with us. I'm just wondering, before I open this floor to ask questions, can I ask one question about what is the flow conditions and then also the local water depths and the wave conditions? I'm just wondering whether some other project may like to collaborate as well.
Yes. So hang on, let me just come back to the site diagram. So we're at the top end of the Milford Haven estuary in Milford Haven. And it's quite a large test area. It's about 1 kilometre in length. We're using the far western end of the site because it's the deepest water. And we think it's about 20 metres at high water, maybe 15, 16 at low water, where we are above a sort of sandy, gravelly seabed. And it tails off quite shallow to the underneath the cliff to the south side of the platform. There are other sites within the Meta family which have larger wave climates, for example. So if you're looking for wave climate, go somewhere else. So it's pretty sheltered. There is a little bit of fetch on it, but not much. But yes, very much available. Flow rate about 1 to 1.5 meters per second, typically 1.8 on a spring, particularly when there's rainwater flowing downstream as well. Slightly faster on the ebb than the flood.
Okay, thank you. Any questions from audience? So please feel free. I'm just wondering how can you unmute people on this Zoom platform? And also you can type your question in the chat box as well, if you like. And also you can just speak up to ask any questions to Ian. We can have a couple minutes before we can invite Stuart to present his research.
I think people can unmute themselves now. If you have any questions, you can just unmute yourself. Yeah.
Thank you for your help. Yeah. So, Ian, before other people ask questions, I just continue. How many years have you been working on this device? I guess you started with numerical concept,
Yes, so
laboratory.
probably about 2 or 3 years ago, I ran a group design project looking at this technology. So I'd already had a concept on paper, some drawings and some sketches and some ideas myself. And I gave it to a group of master's level group design students, and they came up with the first SolidWorks. We've been working on this for about a year in terms of actually turning their concept drawings into something we can actually deliver. So yeah, so it's been 3 or 4 years slowly, in the last year more intensively.
Yeah, I know you have been working on tidal energy for many years, and also many different devices as well. You have done another sea trial in a similar area as well. I'm just wondering, what's the advantage for this particular device compared with your previous other tidal energy devices?
So, yeah, that's a good question. There are some very good technologies out there for grid-connected electricity using more sophisticated systems. So I'm not attempting to compete with anything which is a good quality grid connected megawatt scale device. So this is at a different target market. And what we're trying to do is think about how to keep the system robust. So fixed pitch blades, the wet running bearings. There aren't many systems which are using those types of technologies. Most commercial technologies now have a variable pitch system, which is better, but expensive and needs looking after. And most systems have some sort of rotary seal, and then everything else is inside a sealed box. So that's what's different about it, is we haven't got that sealed environment with bearings and motors and gearboxes and all the other stuff that you need to make energy effectively. So I don't know if it's suitable for large scale, but at this scale and for this type of environment, where we want somebody to be able to fix this with a mallet, I think it's appropriate technology. That's what we're trying to do. But the parallel thing we're doing is we're building a platform for researchers to be able to access relatively cheaply, so that we can take other measurements and do other things with it. So there's like a dual purpose for this technology.
That's very good. Thank you for opening up this opportunity for others to be able to use the platform as well. I now have a question from Ali. The question is, would you please explain how you fix the platform with moorings? Because that is a huge flow. So what are the tools and the methods you have used?
Okay, mooring lines all the way. Moorings are on this one. So mooring lines, we have, it's a gravity anchor with some chain on the seabed and a catenary layout. We have a pair of moorings each side, and those come to a single line, and we have a single line onto the platform. So it's a Y mooring arrangement. We did some design work, and then after discussion with Meta, we've actually contracted a consultant company to check our calculations. So Yestin and my team has designed those moorings, and then they've gone and checked his numbers and basically upgraded it. So we've used some fairly simple design calculations to do that, using friction and weight and thrust. It's not a big turbine, so it doesn't need massive moorings, but they're fairly substantial.
Thank you, Ian. Yeah, I guess Ali is happy with your answer. Thank you very much, Ian, for your contribution. It's a very interesting project. Everything goes well with your sea trial, and we'd love to hear what's going on afterwards.
Yeah, I'll come back in June and tell you all about it.
Okay, that'd be great. Yeah, I hope that we can see you in Bath, and June. Thank you. So now we come to our next speaker. Stuart, please can you share your presentation? So Stuart's title is Challenges and Opportunities of Bio-Based Turbine Blades for Marine Energy. Dr. Stuart Walker is from Exeter University, and he was the chair of a previous year's PRIMaRE and also ran a very successful conference. So it's a hard job for us to follow this year in Bath. Over to you, Stuart.
Thank you. Can I just confirm you're getting the slides rather than the notes? I never know which screen is which.
Yeah, everything okay.
You're getting the right one. Perfect. Okay, right. We'll go for it. Okay, so yeah, thank you. So yeah, I'm going to talk a little bit today about, as I called it, challenges and opportunities of bio-based turbine blades for marine energy. So looking at some kind of biologically based materials and talking a little bit around that, some work that we've done and some sort of highlighting some areas for other people to take on the work in the future, I think. So first of all, to kind of look at the reason for doing this work. So as we know, turbines, so tidal turbines in this case, and wind turbines more generally, provide electricity with what you might call a low specific greenhouse gas emission. So low emissions per kilowatt hour of electricity generated, say, compared to fossil fuels or anything else. We know that obviously, but the turbine itself does have some environmental impact. The manufacturing, as you can see along the bottom there, the materials required, the manufacturing processes, things like transport and so on. So at the moment, to use a turbine, it has a positive impact. But when we look in future, if you're replacing the electricity in a country that has a very low emission electricity grid, you need to kind of think about the embodied energy and the embodied impact of the making of a turbine in order to make sure that you actually have a net benefit, so that you're replacing higher impact electricity with lower impact. So materials are one kind of way that we can keep progressing and look to kind of reduce the impact further. So that's kind of the reason for doing the work. So if we look at turbine blades, so again, we've got some wind and some tidal. Just to give you kind of a rough idea, so the blades on a tidal turbine, so on something like a 9-meter blade, this is looking at a single blade of the type in the lower right, the Atlantis type there, rather than the old Sabella design there. But yeah, so the kind of wind turbine looking style tidal blade, that's probably about 3 tons worth of blade. So obviously 3 of them adding up to 9 tons in total. This is all the kind of the problems and the opportunities that I'm going to talk about today are shared with wind. So I'll keep kind of referring to wind a little bit as well. So obviously in a wind turbine, you've got a much bigger blade, a sort of more slender design, so and less mass per unit length. But those blades, when you get up to the big 100-meter plus blades, you're starting to look at over 50 tons. So there's huge amounts of mass of this material up there and down there, as it were. Yeah, so working out from sort of broad projections of the sort of installed capacities that we're going to be looking at by 2050, you can see that we're looking at the order of certainly of megatons of blade mass only going into operation. So it's a big potential opportunity to do something with. So blades, the reason for kind of focusing on blades in some senses is because a lot of materials in a tidal turbine are quite recyclable. So a lot of ferrous metals, a lot of steel and such like can be recycled relatively simply, and we know how to do that obviously very well. Blades are one example of where composite materials are used. So carbon fiber and glass fiber reinforced polymers tend to be the kind of most commonly seen ones. So I'm just going to go over quickly a composite material and kind of the fundamentals of what that is. So this is in very simple terms. You have a fiber element, as you can see there on the left, so that's a roll of glass fiber, and you have a resin element, as you can see on the right. That's an example of an epoxy resin. So you can see this image obviously shows a very kind of small scale, a kind of DIY scale, if you like. So you can see there that those mixing those two components together is how we get a composite material. So we get a glass fiber reinforced polymer or a carbon fiber reinforced polymer by mixing those two together and a curing process. So that's at that scale. It's actually exactly the same at a big scale, so a turbine blade scale. So you can see on the right there, that's a huge, I think that's the Siemens factory for a wind turbine blade. So you can see that's the rolls of fiber there in the inside of the turbine, and they're being laid up with the resin to make the composite material. And similarly on the image on the left, it's a tidal blade. So this is after that process has been undertaken and coatings and things have been put on now. But you can see it's fundamentally the same material, the mixture of those two parts. So as I said, one of the problems with these kind of materials is that they're very difficult to dispose of. So not recyclable like a steel or another metal type product. They're quite hard to get rid of. So at the moment, they are effectively kind of a single-use material at the moment. So there are, in theory, three disposal options. So the first two, landfill and incineration, I'll come back to, just to cover kind of repurposing the bottom one at the end. As you can see there's some very nice kind of ways of reusing these leftover blades and things, but really those are vanishingly small, particularly when we talk about the megatons of mass that we're going to be putting into the system in the coming years. So they're a kind of a nice thing to do for a few blades, but they're not really a major part of the kind of disposal route, which leaves us with landfill and incineration essentially. So landfill, so a composite material is relatively inert. It can be buried in the ground and it can kind of remain there and probably not cause us too many problems, but then becomes a problem of land use and of the resources that are used to put those things in there, and the land that's occupied by those huge amounts of mass that we're going to be talking about. Incineration, the materials can be incinerated, can be burnt, and we can probably extract a little bit of energy back from the heat that's generated during that process. But it's a very energy intensive process to incinerate a reinforced polymer, and we don't get anything material wise, we don't get anything back at the end. And it can also cause some problems with releasing. It has air quality problems and toxicity issues and things. So what's released from the incineration, so that's not an ideal option really. So in a minute we'll look at some possibly potential other routes. So first, just to do a bit more sort of simplistic looking at composites. So an ideal composite material that would allow us to dispose of it in a sensible way would be if we could have the fiber and the resin, mix them together, get our composite material. We could then use our composite material, and then if at the end of life we could then separate it back into the fiber and the resin, we could then either rebake that or treat those in individual methods which allow us to recycle them or reuse them or whatever. The problem is at the moment when we mix the resin and the fiber together with an epoxy resin that as is used most of the time at the moment, so that's a thermoset resin, we get our composite, those two parts together, but we're not able to then separate that back. So what we end up with is we can break it down into smaller parts, but they're still a mixture of those two elements, which limits the disposal options and sends us down the route of those two that we talked about. So in theory, if you had a bio-based composite that was made of both a bio-based fiber and a bio-based resin, so something natural in both of them, you could then make that into a composite and use that in your product. We still wouldn't be able to separate the two and take it back to the individual elements. But then when we broke that down, we would have a single material type. So in theory, we could probably then look to compost that or to do some sort of biodegradation, which then might give us a small amount of benefit and then allow us to regrow some bio-based materials in future. So that might be a potential option. There's also what I'm calling here separable composites. So if we use a thermoplastic resin rather than a thermoset resin, so that's a resin that can be heated and separated. So the reason that's not widely adopted at the moment is the ultimate polymer tends to have lower mechanical properties when this type of resin is used. But it does have a major advantage that when we use it there, probably with the help of some sort of separation agent or some process, we can actually split it back down into the two elements. The problem that we then have is that the two elements aren't as good mechanically as they were originally, so we can't actually then reuse it at the same level. We might be able to downcycle it to use it for a different material or a lower level use, or we might just be able to separate the two elements and then send them down individual recycling and composting. So if it was a bio-based material or some other kind of disposal route. So that's a route potentially to more efficient disposal. Okay, so to look a little bit at some bio-based options, so I'm going to talk first a bit about bio-based fiber and then a little bit about bio-based resin. So bio-based fiber materials, so instead of a glass or a carbon, we can use We can use various bio-based materials. So flax is the most common one due to mechanical properties, has advantages over the others that I've shown there. So flax is probably the most viable. So that's a plant that's grown, a flax plant that's grown, as you can see in the top left image. It goes through various sort of processing stages, harvesting, processing, and then we end up with, as you can see in the bottom right, a fiber material, which we can use in the same way effectively as a glass or a carbon. So we can use, as I've said there, we can use either type of resin, so either an epoxy, a thermoset, or a polyester thermoplastic. We can also have a bio-based resin, either with the bio-based fiber or in a glass fiber usage. So similar to how we can make a bio-based polymers, so plastics, so we can make PET and HDPE, for example, from bio-based sources through breaking down things like sugarcane and forest residues and things like that. We can break them down into the chemical building blocks that we use to make these polymer products. So we can go through that process, and we can get 100% bio-based resin. It's currently much more economically viable to have a mixed resin, so to a partially bio-based resin and partially fossil-based, but the 100% bio-based resin is in theory possible. So a little bit now I'm going to lead us sort of towards a case study that we've done on some comparison of materials. But first of all, just to look at a kind of idea of the life cycle of a fossil-based composite material and a bio-based composite material. So this would apply equally to a polymer or something. So if you look at this kind of indicative graph, so the red line here is showing us the cumulative environmental impact over the lifetime of the product, essentially. So here we're talking about a fossil-based product. So the top of my little oil derrick image is missing there, but you can see in the first step that's the extraction of the oil from the ground. We then go through various processes, refinement, manufacture, all of which use energy and emit, cause environmental impact, so emissions and various other impacts. So that red line grows and grows over time, and we get to use, and then at the end of life, we, depending on how we treat it, we have various levels of emission at the end of life. You can see that in the fossil case, that impact naturally builds up over time. So in a comparative bio-based case, you can see, so the horizontal axis is actually through the middle here. If you notice, it's moved up, and that's because during the growth phase, so the first stage of the bio-based material, so when it's a plant growing, it's actually absorbing atmospheric CO2. So it's taking in greenhouse gas from the atmosphere, and that's stored in the plant. Then as we harvest it and again go through manufacture and use in various processes, we essentially use up that. So we don't use up that emission, but we have in net terms, we use that up. So we end up with maybe around the manufacture phase, we end up with a net zero emission, and then as we go through use and end of life treatment, we again cause some more impacts. But if we can reduce those middle phases sufficiently, we can lower that line down, and you could in theory end up with a material that can get to the use phase and still have a net negative emission. So it can be effectively sequestered greenhouse gas at the point of use, in theory. So this sounds great for bio-based materials, and we're talking about challenges and opportunities. This sounds like a great opportunity. So to counter that, let's have some challenge. So the major challenge really of using these materials is a lot of it is down to the performance, so the mechanical performance or the performance in use. So you can see here, this is for a flax reinforced polymer compared to carbon fiber and glass fiber, so C and G FRP respectively. So you can see the carbon fiber is basically a lot stronger than either of them. The glass fiber and the flax are not dissimilar really. So it's not a terrible performing material, the flax reinforced polymer, but it does mean that we're likely to need quite a lot of mass in order to achieve the same level of performance as we would have in, say, a carbon fiber. So we can't have a lightweight carbon fiber blade. We're going to need more mass, and bringing more mass means we're going to need more. It's going to have more impacts because we're going to do more processing, we're going to do more transport, etc. So this brings us to a case study that we did as part of the Tiger project. So little bits of this I've presented before, so apologies if people have seen bits of this. So we compared basically the environmental impact over the lifetime, as I've just shown, for a tidal stream turbine blade based on, we looked at a few different materials, but here we're looking at glass fiber, carbon fiber, and flax. Yeah, over a 20-year lifetime. So the first step we did was to work out what mass of material you would need to have comparative performance to a glass fiber blade. So you can see there we end up with a glass fiber blade about 2.5 tons, a carbon fiber blade of about a ton, and a flax blade about 1.5 tons. So, excuse me. So that looks quite good for the flax in theory. It's not as heavy as the glass fiber needs to be, so that's an advantage. In our model, we looked at a flax and polyester resin composite. So that's a separable resin, as we talked about before, so a thermoplastic resin mixed with a flax fiber. So in order to separate the two at the end of life, we need to use this thing called a recovery solution. So the properties of down at the bottom, if anybody's interested. This is from information from Aditya Birla, who helped us with this study. And the recovery solution allows you to separate the two and then to treat them in different ways, as we showed earlier. But it does have its own environmental impact because we have to make that product. It has 25% acetic acid, so there's a reasonable environmental impact in making that separation product. Manufacturing process, we don't really need to worry about. This is just to show that we use the same manufacturing process. A common method, VARTM, was used in all the cases that we compared in our study. And so to move on to some results of the case study. So first of all, I have results for glass fiber. This is a glass fiber blade made, used, transported, and then at the end of life is treated by being sent to landfill. So you can see there, for the single blade, its total impact is around 15 tons of CO2. You can see that the majority of that is from the materials. There's a small bit from manufacturing. Transport is almost negligible. And then at the end of life, we have a bit of an impact there. So if you then compare that to a flax blade, so that's the flax polymer that we talked about previously. So this is treating the flax in exactly the same way. So even saying that you send it to landfill at the end of life, which isn't necessarily what you would do, but as a comparison, that shows us. And the flax blade in that case has about a 10-ton impact. So that's a good advantage for the flax blade, it would seem. If we consider the carbon fiber, it doesn't look good at all, really. So that's because even though it's a lighter blade, the impact of the materials is very significant. And as you can see, the manufacturing is low, the transport is very small because of the light weight. But then when you look at the end of life, the end of life treatment through landfill, there's a lot of risk of carbon fiber in landfill and a lot of embodied emissions in order to process that and to try to avoid any kind of risks of landfill leakage and things. So it doesn't look so good for the carbon fiber in this comparison. And then as our final result, if we look at the furthest right, there is the flax treated through biodegradation. So this is kind of what we imagine would be the ideal process. So this is making the flax blade, manufacturing it, transport it, use it, and then at the end of life, separate those two elements. And the flax fiber would be treated by biodegradation, so it would be composted essentially, go back into the soil, and the resin can be treated as a polymer. Unfortunately, that has a slightly higher impact than even the flax landfill treatment. So obviously, we should not consider these in isolation, but it shows us that the manufacture of that recovery solution that's needed to separate the two is actually quite a significant part of the overall. So that's why the yellow bar there is a bit higher. So as I said, we shouldn't just look at these kind of results in isolation. So they show us about the greenhouse gas impact, but we should also consider a kind of a wide range of other impacts, such as land use is kind of a key one, particularly when we're looking at products that we're growing and using land in order to grow. So a comparison here just to show. So this is, apologies, it's from a different paper, so it has slightly different comparison in it. But you can see compared to a glass fiber blade treated by incineration or landfill, if we look at a bio-based blade, the land use in square meters per unit turbine blade is significantly higher for the bio-based blade. So that's obviously because we're growing stuff in order to make that blade. So it shows us that although we might have a greenhouse gas emission saving, we have a land use penalty effectively. So it's all part of kind of the combined impact that we should take into account. Okay, so the results of the kind of case study that we talked about, as I've just mentioned there, really, so the sort of the source of the feedstock is important. So that land use impact is high because we say we're growing that product specifically in order to make the flax, to make that blade. If it could be some sort of waste, if it could be a waste product from something we're growing anyway, then that land use would be, there'd be no additional land use. It would be kind of double using the land use that's already there. So that would be a great way to go. On the other hand, if we stop growing food crops and we start growing flax instead, and we start limiting food supply and things like that, and perhaps even also causing additional water use and all other impacts like that, that would be pretty significantly negative impact. So we should there's growing the product doesn't have to just have a single impact. It can have a whole range of impacts depending on how we do it and how well we do it. So yeah, to kind of work towards a kind of conclusions soon. So at present, bio-based blades do seem to offer a small improvement in impact versus current options, not without their disadvantages. Needs to be looked into further, which is currently ongoing at PRIMaRE, as Ian mentioned, for example, and various other places, looking at the impact of marine performance. So the impact of water uptake, for example, on the performance of a blade. So if you have a blade that's in the water for 20 years, will it still be performing as well at the end of life? It appears that perhaps not, but that needs to be that work is ongoing, as I say. So finally, economies of scale and possible kind of disposal regulations and limits on landfill might bring these materials to the fore again, and those none of the issues are unsurmountable. So there's definitely potential for bio-based materials. But one key thing to kind of note is that, as I said, in order to get the advantages of the bio-based materials, we really need to be able to separate the polymers. So looking at those thermoplastic resins that allow us to separate the two, which then does raise the possibility that if we're going to do that anyway, if we're going to separate the two, then we don't necessarily need to be using bio-based materials. If we can separate the two, then we can look to use other options. So provided the two materials can be separated, you can then go along different end-of-life treatment routes. And just to kind of conclude, that seems to be where the wind industry is going at the moment. So not really looking at bio-based materials, but looking at polymers that can be split and treat the two in different ways. Yeah, whether that be conventional kind of disposal routes or gummy bears. Yeah, so finally to conclude, opportunities and challenges. So opportunities, bio-based materials, they do allow different end-of-life treatment methods, so you avoid the need for landfill or incineration. That uptake during growth can be a big advantage because you can lower inherent greenhouse gas emissions if you can reduce the processing required. Impact of that additional processing will fall as electricity is decarbonised. Also depends where in the world you do it. If you do that processing somewhere that has low greenhouse gas emission electricity available, then you can make a big difference. Yeah, and that allows the potential for future greenhouse gas sequestration. Challenges, economies of scale as always are needed. So we're competing against a sector that's been doing this for a long time and has a large, significant economies of scale. So that's a potential improvement. Conventional materials with separable resins might be more cost effective. Mechanical performance is already better understood. And that does seem to be the way the sector is moving at the moment. Yeah, and as I've said, source of feedstock must be carefully considered to avoid any kind of land use or food conflict, and again, those additional manufacturing requirements. So sorry, I've kind of rushed through that and still managed to take a bit longer than I intended. So if anybody does have any questions, please fire away. Yeah, and I think that's it from me. Thank you.
Thank you, Stuart. The very nice presentation, and then also I'm really grateful for you both to hate the timing. Perfect timing as well. Thank you so much. So welcome everyone to ask question to Stuart about his research. So probably before you can type your question or you just unmute yourself to ask question. I'm just wondering, have you talked to industry manufacturers? Are they on your side? Are they willing to collaborate to change the way they produce blades?
So yeah, we've spoken to some. So we've spoken to a lot of turbine manufacturers, so the people who procure the blades through the Tiger project, and there's some interest certainly. I think at the moment tidal developers are, they have a lot of not to say a lot of problems, but they've got a lot on their plate already with trying to work through consenting and things like this. So they currently would like a material that you can tell them has good mechanical properties over its lifetime, which is why that kind of ongoing work is important. But yeah, there's certainly, we've had really good engagement from some of the companies in the sector who really want to kind of, who really see this as something that we can do to push tidal ahead of wind, perhaps, to say that we've solved this problem from the outset, and that, well, it's not something that we're going to kind of look at down the line, but our devices are environmentally benign from the start. So we have good involvement.
Good luck. Thank you. Any questions from audience? If not, so I have many questions myself. This is quite interesting topic, and also you mentioned that in the early your presentation you said that is mainly for offshore wind. Are you thinking this can be used for both offshore wind and also tidal energy? And what are the challenges for this blade exposed in air and also underwater?
Yeah, so I think there is definitely potential in both. I think in some ways using it for wind is easier because you avoid the problem that I was talking about the water absorption, which does seem to potentially be a thing that will need to be overcome for tidal blades, whereas for wind blades it's obviously less of a problem. I think as you've seen, the wind industry is now dominated by some quite big companies, and they seem to be going down that route of looking at the separable resins that allow you to then treat the products in a different way. But even if you do that, you still then have in the best case, if it goes brilliantly, you still then have a glass fiber that isn't mechanically good enough to reuse in a wind turbine. So you then still have to find something to do with it. So I wonder if once they've got that stage sorted, they might then look at using a bio-based blade that gets you the next stage further, because it means that your fiber then you don't need to find a reuse for your fiber, because then it can be biodegraded or composted. So yeah, I hope that in future the wind sector will kind of come on board a bit more. Yeah.
Thank you. I now have Ian a question. He asked, the material properties are different. So do you need different amounts of materials? Is this factored into your results?
Yes, that's absolutely right. Yeah, the material properties are different, and you do need different amounts. So yeah, that's in our results. I had that comparison of the different mass of material you would need. So we have taken that into account through a finite element model. The only caveat with that would be we just did that for the beginning of life, so we didn't include any kind of degradation. So you could argue that maybe in 10 years' time the glass fiber would still be performing as well, but maybe the bio-based, we don't know, but might not be performing as well. So we might need to build in a bit of kind of redundancy in the early life that then allows it to keep performing well over the whole lifetime. So, but yeah, that is included in our calculations.
Thank you. I have another question in terms of bio-based material. So you need natural fibers. Do you think you can find a massive amount of those natural fibers available to be able to be used to produce turbine blades, or whether if you use that material, whether that will hit other sectors or other areas as well?
Yeah, no, it is it's certainly, you do need a lot of land to grow the right amount. I mean, these are relatively long-lasting products. So although you need a lot of it, once you build a turbine and install it, that the blade will be in service for maybe 20 years or something. So it's not like you don't need to produce it at the volume that we produce, say, plastics at the moment, where there's a lot of single-use materials and things. So there is, you would need a significant amount of land to grow these crops and to do it, but I don't think it's an unsurmountable problem. I think because of the kind of the timescales involved, and these are relatively, really quick growing products, so they can be grown relatively quickly and then used and regrown yeah. But the avoiding that competition with food crops particularly is a kind of there has to be a solution for that. These things can't kind of replace food crops or be grown in areas that compromise food crops. But yeah, I think as well, I'm not an expert on the kind of biological bit of it, but I understand as well that these can be grown in some kind of marginal areas where food crops don't grow quite so well. So it could be that we can avoid the conflict with food crops by growing them in these kind of more marginal areas where food crops wouldn't be grown anyway.
Thank you, Stuart. So now it's 2:01. We had two great presentations for our first PRIMaRE seminar series. That is great. Thank you so much for volunteering to present in this first PRIMaRE seminar. Our next seminar, that will be on the 18th April. We have another two great speakers. So one is Professor Deborah Graves. She's the fellow at Royal Canadian Engineering and also director of Coast Lab in Plymouth University, and also director of SuperGen ORE funded by the EPSRC. So she's the one speaker, and another speaker will be Dr. Stuart Herbert. He's a Chief Technical Officer in the Celtic Power Limited, developing floating offshore wind. So but for now, so we're going to meet you in April, and also welcome to submit your abstract for our 10th PRIMaRE conference that will be taken place in Bath in June. Thank you so much for coming to the seminars, and also thank you to the great speakers, Ian and also Stuart, for the excellent presentation. Thank you. See you next time.